Chapter 6 and 7 are on nuclear physics. What you find here is in chapter 6, we're really introducing the ideas of nuclear physics, and we'll finish up with radioactivity. Nuclear forces are quite different than the atom. Radically different, actually. And so if I was to give you an overall view of where I'd like to go, I want to talk about nuclear forces. And it turns out that forces are the worst way to talk about problems. It just really is. What's more important is energy. Energy is really the key to understanding the nucleus. So we'll start off with nuclear forces, and then we'll switch over to nuclear binding energy. And one of the big questions that we have to answer is that I shouldn't be talking about the atom, I should be talking about the nucleus. Okay, so the question is, why are some atoms, but I really shouldn't say atoms, I should say nucleus, right? I should be saying the nucleus is what we got to handle. So why are some nuclei stable while others are unstable? And you're going to see that the way we visualize this in nuclear physics is there's something called the band of stability. And you're going to have to become an expert at the band of stability. And you're going to see that this can also go by a different name. So right now we'll talk about it in terms of the band of stability, but what you're going to see here, but when we get to radioactivity, it's actually better to refer to it as the valley of stability. And that turns out to be really important. And when you're looking at the valley of stability, it's easier to talk about radioactivity. And every time people hears the word radioactivity, a lot of people get like, I don't know, they get funny in some sense. And the reason why is because they don't know what it is. And you're going to see that the three most basic types of radioactivity is alpha, beta, gamma. Those are the three basic ones. And from here, you might say, so why is radioactivity so important? Well, it's vastly important for numerous reasons. If you look at smoke detectors, for example, that's an example of radioactivity. If you do some type of imaging, most of the imaging of the human body is done with radioactivity. And, there's these other ones. Probably one of my favorite ones of the radioactivity is that you may realize this or not, there have been 5 mass extinctions. And when I say mass extinctions, the one that most people think about is the one that happened 65 million years ago. Actually, that's not even the biggest one, but there have been 5 mass extinctions here on Earth. The question is, how do we know this? And it becomes one of the most important tools used by archaeologists to actually look at what happens. I mean, God, there's just so much here. And to try to do this in one chapter, well, it's hard. And so one of the things that we should do then is that we should really start talking about the most basic of these and then expand. By the way, there's another chapter on this, chapter 7. And it's, like I said, it's huge. We'll look at other nuclear processes. But the first thing that we should talk about is the forces of the nucleus. And when I think about the forces of the nucleus, one of the things that I would say here is that if we think about the forces of the atom, we know that the forces of the atom are electrical forces. Okay, so we know that the forces of the atom, let me be careful, the forces of the electrons in the atom are electrical. And really the key thing here is how electrons interact with each other is quite different. In fact, radically different than how protons / neutrons interact within the nucleus. And what you're going to see here is that I've said this in the past, and I'll say it again, the word chemistry, and by the way, it's also physics, physics of the atom, as they say, is how the electrons rearrange themselves. It's always about how they rearrange themselves. So how do they rearrange themselves? In nuclear physics, it is also how protons / neutrons rearrange themselves, but how they can change from one type into another. Through the process of radioactivity, a proton can change into a neutron. A neutron can change into a proton. So it really changes things quite radically when you start to look at this thing here. And so we've said a couple of things here, okay? And what we've said in the past is we look at something like this. We've said here is that if I was to give you an analogy of the situation, what do I have? The analogy is that we said here is that Rutherford's model, maybe I should say planetary model, is a bad model. Is a bad model of the atom. So when I think about this, I have some nuclei. And we know that the nuclei is positive. And in this model, we know that we have an electron. And this electron is whizzing around in a planetary orbit. We know that this is a bad model. In a very analogous way, in nuclear physics, there is another bad model of the nucleus. Okay, and what I mean by that is that the depiction we have of the nucleus, and by the way, I perpetuated it, and I'm not even sure if I'm even going to address this issue here in this course, because why? It gets complicated very, very quickly. So if you see a picture of a nuclei, let's say that looks like this, or these are the protons, these are the neutrons in here, right? So in this case here, I'm going to say that, yep, here's a neutron, and then here is my proton. So this is what I would call a proton. This is what I would call a neutron. If you see this image of the model of a proton, guess what? It's not very good. It's a terrible model. And just to show you what I'm talking about, all I did here was do what? Let me go share my screen with you so you could just see. Look at this. I just typed in nucleus of atom, and look at all these pictures that they're showing of the nucleus. That's my point. It is not a good model. And the question is, you might ask the question, so why are you teaching me this if, it's a bad model? Well, here's what we know. Neutrons and protons. So what we know here is that neutrons and protons in the nucleus have a shell model. And this model's more complicated than it was for electrons. Furthermore, these neutrons and protons can change into each other. As a consequence, just having this picture like this doesn't do it any justice. But that's what we got to deal with for right now. We could still learn a lot about it, and we will. So let's keep moving on here. So when you look at this picture here, and here's another reason why this model is not so good, and probably the biggest reason. This model of the nucleus is missing something big. And the reason why that is just so, just let's say by looking at the electric forces of the proton, there is a big problem. And the big problem is it shouldn't exist. Okay, it shouldn't exist. Right? So when I'm looking at this, it shouldn't exist. So if I think about this, let's take this image of our bad nuclei model. And when you look at this thing here, look what's actually happening. There's electrical repulsion. In fact, as this thing gets quite large, that means the nuclei gets quite large, you find that the electrical force is trying to blow the nucleus apart. So what we're saying here is that there is a huge electrical repulsion inside the nucleus by the protons. So what you're seeing here is that the electrical forces, which I'm going to call E forces, the electrical forces are trying to blow apart the nucleus. So the question is, what's going on? Now we know that many nuclei are stable. And remember what we mean by stable. Stable means at least one stable isotope, at least one stable isotope lives forever. And as far as most of the atoms have stable isotopes. And so what I'm really saying here is that if I look at atoms 1 through 82, so this guy's what? Hydrogen. This guy's lead. Most of these have, all of these have at least one isotope. Many of these have multiple isotopes that live forever. So atoms 1 through 82 are stable and not radioactive. So then it begs the question, why is the nucleus not blowing apart? And the answer is that there must be another type of force that prevents this from happening. Right? There must be something else.